All right, chapter 3.2.1 says, when is an inverse not a function? We're going to look a little bit here at inverse functions and inverse relations. First thing here, remember a relation is just a set of points. You can have a bunch of points on a graph there, it's just a list of points. What makes them a function there is when we have, for every input, there's exactly one output, and we'll talk more about that here. So as we look at it here, two relations are inverses if and only if one relation contains the point BA when the other relation contains the point AB. So in other words here, you switch the x and the y coordinates. This was something that you did earlier in chapter 1 when we were doing some review, but even more importantly in algebra 2, you did a lot more with this, finding inverses of functions, using a table, using the equations, and using the graphs. So this part down here just is meaning here when we're switching the x and y coordinates. Say our function has, our function has the point, let's say here, 3, 2. Well, then the inverse of that function is going to contain the point 2, 3. So we were just switching the x and the y values. So starting out here, looking at the graphs of inverses, okay, the first graph we have here is y is equal to x squared, and we know which one that one is. That's the red one here, the parabola that's going up like this. Okay, but then it says we also have the graph of y is equal to positive or negative square root of x. So remember that comes from y is equal to the positive square root of x and y is equal to the negative square root of x. And what that does for us here, right, is it creates this parabola shape that looks like it's going sideways. So these we would consider to be inverses of each other, and we can see it on a graph by looking at their symmetry. Remember, inverse graphs will have symmetry across this line that runs right up through here, kind of diagonally on the coordinate plane, right? The equation of that line is y is equal to x. So our two graphs that we have here, if you think about like the reflection across that line here, if they're inverses, you will be able to see that symmetry. If they're not inverses, then you will not there. But it's just asking here visually, a relation and its inverse are symmetric across the line y is equal to x. That's review. Hopefully that helps you to remember that part of it there. Let's look at this next part. Given a function f of x, its inverse is called, we'll take it here, and this is where we had f, and it looks like it's being raised to the negative first power, but we read this as the inverse of f of x. So we've got f of x here, and then over here we have the inverse of f of x. And if our original is a function, the inverse may or may not be a function. It just depends on the original graph and what it would look like. In order to be able to tell this here, we usually would try to do our vertical line test. So on this here it says, if one or more vertical lines intersect the graph of an equation at more than one point, then the equation is not a function. So if it intersects it at more than one point. If no such vertical line can be drawn, then the equation is a function. So for instance here, we have example here. Now remember, functions are relations. All functions are relations, but not all relations are functions. So if we were being specific about this one on the left here, this would be a function because if I drew vertical lines anywhere on this graph, you notice it only hits the graph in one place. Right? So you see here, as we're going through it there, you could hit it anywhere on that graph. If you dropped a vertical line through it there, it would only hit the graph once. Remember, for each input, there is exactly one output. Now, a relation that is not a function here will be the one that we're looking at here on the right side. So this one is going to be a relation, but it's not a function. And the reason why, when we drop our vertical lines down through the graph, right, you'll see here that it hits once, twice, 3 times on that one. If I drop it down here, it hits it 1, 2, 3 times as well. And then if you look over here on the right side, right, if I draw this all the way down there, it only intersects the graph 1 time. But it's because of these two vertical lines, right, any of those points in there where we have more than one output for each input there. So that would make it just a relation and not a function. So now shown below is the graph of f. It says, is f a function? Well, if we take some vertical lines and drop them straight down through the graph here, you're going to see here that we cannot find any points on here where it intersects the graph. Well, I guess any of the lines that intersects the graph in more than one location there. So this one would pass the vertical line test, and yes, it would be a function. I'm going to get those off there real quick. Okay, so now we're going to talk about how do we graph inverse functions. So the first thing we're going to do here is we have our initial graph here of y is equal to f of x. So let's just collect some points off of this graph here. We're going to say we have the point there at -2, 0, -1, 4, 0, 2, looks like 1, 0, and then 2, 4. That should give us kind of the shape of the graph. And I'm going to go ahead and list those out on a t-chart. So this is our original f of x function here. So we've got, we said -2, 0, -1, 4, 0, 2, 1, 0, and then 2, 4. Well, because we said here with the inverse functions, we would switch our x's and y's. So what we're going to do here is we're going to make a second table over here on the right side. Okay, this is going to be our inverse function. And what we're going to do here is we're going to take this column here from the left side of our original function, right? Those are our x coordinates. Well, if we're switching our x's and our y's, those are now going to become our y coordinates on our new graph. So you can go ahead and just recopy those down. And then what was our y coordinates on our original graph will now become the x coordinates over here. So we're going to take it, we're going to copy those points down. Make sure you keep them aligned with the corresponding value that it was paired up with originally. So we had 0, 4, 2, 0, and 4. All right, and I guess I should have mentioned this before. As you were recording these points on your original graph, you want to make sure you kind of record them in order as you come across them from left to right, or you could go from right to left. That's up to you. But it makes things much easier than when we try to reconnect them on our inverse graph. So let's go ahead and plot our points here. We had 0, -2. We had 4, -1. We had 2, 0, 0, 1, and 4, 2. Now if I just gave you those points and said, hey, connect them there. Oops, I think I put that one up a little too high. Let me fix that. But if I just gave you those points and said, hey, connect them there, it's a little more difficult to just connect them on the inverse graph. So let's just connect them in the order that we had them recorded there, right? So it would be like 0, -2 would be our first point, and then we'll connect it with like 4, -1. We'll connect that to 2, 0. So what should happen here is it should start here, and we're going here, we're hitting this one, and then we're going to hit that 2, 0 on our way to 0, 1, and then on our way to 4, 2. Let me fix that. It's kind of ugly. There we go, and it goes through there. And then we can go ahead and extend this back through there. So there is our inverse graph, and if we look at it here, right, as it's zigging and zagging back and forth, we can tell here that this is not going to be a function, because if I try to draw in a vertical line, you know, like say somewhere right in the middle here, I'm going to intersect the graph at 3 places. So the inverse is not a function. Okay, let's move ahead here to the next part. Now we're going to try to graph one here. We're going to have to graph the original and then the inverse. So given y, graph it and its inverse. Is the inverse a function? Okay, so the first thing here, we've got a graph. We've got y is equal to -1/2 times the absolute value of x plus 3. So remember, that comes from our parent graph, y is equal to the absolute value of x. And that's the one that makes that V shape for us there. So this is one of the parent graphs that you probably graphed a lot in Algebra 2, and we've done, you know, quite a few here already. So I'm not going to make a table to graph my original. I think we can do that without. So when we look here, we've got right now, right, this +3, we've got a vertical shift up 3, and then we've got this -1/2 here. Remember, that's going to act like our slope when we're graphing it. So let's start out here. We know originally our graph had a vertex at 0, 0, so we're going to move that up 3 units first. So now we have a point at 0, 3. And then we're going to use this slope. Remember, this is like the slope. So a -1/2 means we're going to go down 1 and then right 2, down 1, right 2, down 1, right 2, and so on there. And then we're going to reflect it across here and go down 1, left 2, down 1, left 2, down 1, left 2. Go ahead and connect those there so that you have the graph of your function. So now that we have that graph, right, let's take it here so that we can graph the inverse. Let's just go ahead here and record some of the points. We don't have to record every one of them there because, you know, both sides of that graph are just rays coming out from that same point. So they're linear, so you just need a point or two. I'm going to use, let's say, I'm going to use -6, 0. Maybe I'll throw like -2, 2 on there, 0, 3, 2, 2, and then we'll say 6, 0. And now we'll just make our inverse table. So this one is our inverse table, where the other one here was just our original function. And again, just flip-flop our x's and y's. So I'm going to record my y coordinates from here on my x values. So we've got 0, 2, 3, 2, and 0. And then these x coordinates now will become the y coordinates. So we're going to say -6, -2, 0, 2, and 6. And now let's just plot those points on the graph. So we have 0, -6, 2, -2. We've got 3, 0. It looks like we're coming back here. We have the point 2, 2 and the point 0, 6 up here. I think there was a point like right in between there as well, so we'll just throw that in there. And now we can connect them. And this should make our inverse function there. And if you think about it here, again, if we were to take it and draw in that line y is equal to x here, you'll see here how it creates symmetry across that graph, right? Between the red and the blue graphs there. So that's another way you can check to see if your graph makes sense or if it's correct. The final question on this one said, is the inverse a function? And in this case, if we took it here and we drew a vertical line straight down through, right, it's going to hit our blue graph in at least 2 places there, so therefore it is not a function. So no, our inverse is not a function on that one. Now, how do we find the inverse algebraically? Okay, this is something you did do last year. There's a couple methods that were used. We're going to focus this year on mainly just the switch and solve. we reviewed this already a little bit, and we've been using it a little bit here when we were finding the rules for our horizontal stretches and shifts. So let's just go ahead here and look at the steps. To find the inverse, remember we're going to switch the x and the y, and then we're going to solve for y. First thing here, we've got f of x is equal to the quantity of x plus 3 squared minus 5. Let's just go ahead here and change the f of x to a y. Just recopy the equation down. Okay, now I'm going to flip-flop my x and my y. So you see those are going to change, but everything else will remain the same. So as we look to start solving this, right, our options are we could either take the square root or add the 5. In this case, we should be adding the 5. So we should have, x plus 5 is equal to the quantity of y. Oops, see I wrote x there, just kind of programmed to do that. We should have y plus 3 squared. And now we're going to end up taking the square root of each side to undo the square. So we're looking at the square root of x plus 5 is going to equal the absolute value of y plus 3. Remember, when you take the square root of something that's squared, right, there's going to be two possible answers there. We can square two different numbers, the positive and negative versions of something, to get an answer. So this leads us to this point here where we say that we're going to have the positive or negative square root of x plus 5 is what our y plus 3 has to be. And then our last step here, right, is going to be just to subtract 3 from each side to get y by itself. So we have a negative 3 plus or minus the square root of x plus 5 is equal to y. And so that is actually our inverse equation. Okay, now, if we're trying to write that in function notation, remember then we're just going to write it as, the f with the little negative 1 in the exponent, or we read that as the inverse of f of x is equal to negative 3 plus or minus the square root of x plus 5. So either of those answers would be fine. I know what you're trying to do if you just left it as y, but just make sure you know how to do that. All right, the next one. And at any point, if you want to pause it and try to do it yourself and then come back and check it, please feel free to do that. This one says, find the inverse of f of x if f of x equals 3 times the quantity of 2x plus 2 raised to the negative third power. And let's look at this here for a second. This one looks really complicated because we've got this negative 3 up here, right? So we're going to still do the same thing that we've been doing. Let's take it here and let's just take out the f of x and put a y in. So we have y is equal to 3 times the quantity of 2x plus 2 raised to the negative third power. And then we need to switch the x and the y. So we now have x is equal to 3 times the quantity of 2y plus 2 to the negative third power. And now we'll deal with that negative exponent here. Just remember, when we have something that's raised to a negative power, it's just like repeated division, right? So if we just had, say, x to the negative third, we know that's the same thing as 1 over x to the positive third. So we're going to use our properties of exponents here to make that exponent a negative. I'm sorry, from a negative into a positive. So when we rewrite this here, we've got 3 over the quantity of 2y plus 2 raised now to the positive third power. Remember, this 3 is not being raised to the negative third power, so it has to remain in the numerator. Now that still equals x. Okay, so in order to be able to solve this for y, we can't have y down in the denominator. So let's take this here and let's just treat this like this is a proportion, right? We've got a fraction that equals a fraction, so we're going to do our cross multiplication. So we're looking at x times the quantity of 2y plus 2 to the positive third power is equal to 3 times 1, which is just 3. And now we're getting closer to what we want, right? Can't have this x out here on the outside, right, if we're trying to solve for y. So let's get rid of that x by dividing each side by x. So we now have that 2y plus 2 raised to the third power should be equal to 3 divided by x. And you probably got the hang of it by now, but let's just see. We're going to undo our cube here by taking the cube root of each side. So remember, with cube roots, because it's an odd root, we don't have to worry about the whole plus or minus thing, right? This doesn't happen. This is only with, more or less our even exponents there. There's actually even more to it there, but we'll talk about that later on. So, if I have the cube root of 8, right, that's equal to 2. And if I had, say, the cube root of -8, that would equal -2. Why? Well, because 2 times 2 times 2 gives me 8. -2 times -2 times -2, I guess I should put parentheses around those, would have to equal -8. I can't get positive 8 from multiplying my -2's when there's 3 of them. And same thing there, I can't get the opposite sign. So what we end up with here is 2y plus 2 is equal to the cube root of 3 over x. And now it's just a two-step equation. We're just going to subtract our 2 from each side. We've got 2y is equal to the cube root of 3 divided by x minus 2. And then we're just going to divide each side by 2 to get y by itself. So y equals the cube root of 3 divided by x minus 2 divided by 2. And don't worry about simplifying it any more than that. We just needed to get this y by itself here so that we had an expression to use here. If we wanted to rewrite that in function notation, we'll just write that one more time. We'll say the inverse of f of x will equal the cube root of 3 over x. Remember, that's all under the radical there. And then we have minus 2 over 2. Now, there are several variations of ways you could write that answer, like I just said, but let's just go ahead and we'll stick with that there. If you have questions, make sure you mark them down, and I'll gladly answer them in class. Last one here. So it says, find the inverse of f of x if f of x equals 2x over x plus 2. Now, this one's probably the one that's the most different from anything you've done so far in terms of finding inverses. And the reason why is because we have an x in the top and an x in the bottom here. Again, though, we're going to treat this the exact same way we've treated the other ones. We're going to take out f of x, put in our y. And then our second step here is going to be just to flip-flop our x's and our y's. So we should now have x equals 2y divided by y plus 2. Now with this one, again, we've got a proportion if we look at it that way, right? We've got a fraction equals a fraction. So let's just go ahead and cross multiply one more time. So now we're looking at x times the quantity of y plus 2 should equal 1 times 2y, which is just 2y. In order to get our y's by themselves, we have to get all the y's on the same side, right? So before we can do that, we're going to have to break this y out of the grouping symbols. So we're going to have to take this x and distribute it through so we can remove those parentheses. What it should look like now is xy plus 2x is equal to 2y. And again, to get our y's all on the same side, let's just go ahead and subtract an xy from each side. So 2x is equal to 2y minus xy. And this is an important step. We've already done a problem like this in your homework here earlier, I believe it was last chapter. But when we're trying to solve these for the specific variables here, well, when we have two y's here, we're going to have to do something to make it one y. And this is where we need to factor out like y as a GCF, as a greatest common factor. So when we do that there, right, we're going to pull out that y, and we're left with 2 minus x, right? So we factor that y out. We're left with the quantity of 2 minus x in the parentheses, and that still equals 2x. And now it's easier for us to get the y by itself. We'll just divide each side by 2 minus x. So we're now left with 2x divided by 2 minus x is equal to y. Or if we're writing it in inverse notation, we have the inverse of f of x is equal to 2x divided by 2 minus x. And that's it. So if you have questions, please mark them down. Let me know. We'll go through anything that you need help with. But hopefully that will help you feel up to speed with this section. Thanks for watching.